Hello and welcome to EC3030. In this video lecture, we will look into the more details about clocking. So we will introduce the concept of clock skew, and what this clock skew does is this is one of the reasons for timing violations in registers. And when this timing violation happens, there is a serious problem that occurs that is called metastability. So we will look into the metastability as well in this video lecture. All right, so we have had a short discussion about clock distribution networks, and the purpose of the clock distribution network is to make sure that the clocking signal reaches all the blocks at the same time, meaning that say you have a block over here and say you have another block over here. Now the purpose of the clocking distribution network is to make sure that the total path that the clock signal traverses as it goes to this block and as it goes to this block is the same, so that the clock signal arrives at both the blocks at the same time. But as you can see, this is a complicated network and quite often that doesn't happen, and as a result what happens is that there may be a slight difference in the time at which the clock signal reaches different blocks, and that is essentially called the clock skew. Again, clock skew is formally defined as a phenomena for which the same clock signal arrives at different parts of the circuit at different times. So this is clock skew. So let's look at a simple system like this. Now in the first case there is no clock skew, meaning that both of these flip-flop get the clock signal at the same time. So when the clock signal arrives, this input goes in here at the edge of the clock signal, and then it takes delta ff amount of time to reach this input to be processed, so that the input can be converted to process signal over here. So that occurs at the time t equals to delta ff, and then so in the next clock cycle this input is converted to the final output over here. So what essentially needs to happen is that the period of the clock signal has to be larger than delta ff. All right, so now let's say there is a clock skew of delta, right? So now say the clock signal, this flip-flop 2 gets the first clock signal at t equals to 0, and as a result this input goes to the output of this flip-flop at t equals to delta, and then this is converted to the output of this combinational logic at time delta plus delta flip-flop, and in the next clock cycle this output of the flip-flop will go into the output of the final output, and based on this essentially what needs to happen is that the clock signal, the clock period has to be larger than delta plus delta ff. So what this clock skew does is that it actually increases the required clock period by an amount of clock skew. So as a result, if this skew is large, that means that the clock signal, the clock period has to be large as well. So if the clock skew is very large comparable to the clock signal, then there will be a lot of timing violations that will happen. So to avoid this clock skew, different kind of topologies of the clock distribution network is adopted. For example, here what is being shown is an H-tree distribution of the clock distribution network, where the signal comes in, then it goes to these two edges, and then again it breaks into two branches like this. And essentially what happens is that if you do so, then all the blocks will, all the ends of this distribution network will ideally receive the clock signal at the same time. Another distribution is called linear distribution, and in the linear distribution it's like this. There is one central branch and all the small branches, small branch sub branches comes out of this linear network. Now you can clearly see this in a linear network. The different blocks will receive the clock signal at different times. So a linear clock network is actually the worst case, and H-tree is usually very an effective way of reducing the clock skew. Another way of reducing the clock delay, not the skew, delay, is to introduce buffer. Now in one of the previous lectures you have seen that by introducing buffers you can actually reduce the delay in the interconnects. Now using buffer as well, in a tree structure like this you can reduce the clock delay. But essentially if the chip becomes very large, then it's not possible to design a clock distribution network for which the clock skew can be very small. So what is essentially done is that in very large chips is it is divided into a number of different clock domains, and this technique is called globally asynchronous but locally synchronous scheme, and each of the clock domains has its own clock signals. The frequencies can be the same but their phases may not match, and the way each of the clock domains interact with the other clock domains is through a synchronizer, and this synchronizer tries to make sure that there is no timing violation that occurs when these clock domains tries to interact or exchange data. So we will look into the synchronizer in the later part of the video lecture. Alright, so now let's look at the timing violations. Now in one of the previous lectures we said that there are two important timing requirements for any flip-flops, and that is the setup time and the hold time. It essentially means that when a clock edge arrives, the input has to be stable for TS amount of time, setup time, before the clock edge, and the input or the data also has to remain stable for a duration of TH, the hold time, after the clock edge. And if you, so in the next slide what we will see is that what happens if this timing requirements is not maintained, meaning that what happens if the data changes during this time region around the clock edge. Alright, so first on the left we are seeing the case where there is no violation. For example, the input D goes from 0 to 1 or VDD at this time, and the clock arrives after some time such that there is no timing violation here, and as a result after the clock signal arrives, after some delay, the output Q will just take the value of D. So basically the Q will change to a logic value of 1, or the voltage at the Q will change to VDD after td amount of time of after td amount of time after the clock has arrived, after the clock edge. Alright, so now let's consider the case where the input actually changed right around the time of the clock edge, and as a result what will happen is that the Q, rather than going to VDD, basically rather than taking up the value of the input D after TD amount of time after the clock edge, it will go to an intermediate stage, and this can be VDD by 2. So the input, rather than going to VDD, it goes to VDD by 2 and it stays there for some time, and then finally it may resolve into either a logic 1 state or VDD or a logic state of 0 or voltage of 0. Now at this point so this is what is called the metastable state, and once it goes into the metastable state, it has an equal probability of going into a logic state 1 or logic state 0. Now when it goes into the metastable state, the goal is to make sure that it quickly goes into either a 0 state or a 1 state. If it does not go quickly to 0 state or 1 state, this metastable state will propagate into the next whatever there is, whatever this Q feeds to. This metastable state, this VDD by 2 state, will propagate through the entire logic block and really mess up the entire digital system. So the goal of metastability prevention schemes is to make sure that this metastable logic state or the metastable voltage level does not propagate into the rest of the circuit. The goal is not to make sure that it follows D. Rather, the goal is to make sure that it quickly settles into 0, logic state 0 or logic state 1 as quickly as possible. It quickly goes out of this undefined metastable state of the output. Alright, so here is an example of a metastable state of a D flip-flop. Here is the oscillogram and this green signal is the output. Now essentially what happens is that it went to a undetermined state for some time, and then finally it goes to a logic state 1 or logic state 0 over here. Now all these different curves represent different instances of the input, meaning that this timing violation was created a bunch of times, and all these states correspond to different metastability conditions. And essentially there is a characteristic time, and the characteristic time tau essentially means the on average how long the duration of time that the flip-flop takes to resolve from the metastable state into a logic state 1 or a logic state 0, and this is an average number. So essentially it says that on average the metastability will be resolved within a time tau. So this time tau is called the settling time of the metastable state of a flip-flop. Alright, so one way of resolving the metastability, not resolving per se, rather a way of making sure that metastable state is not propagated into the rest of the circuit, is to use a synchronizer. Now what a synchronizer essentially is a bunch of D flip-flop connected in a cascade. Now let's try to explain what a synchronizer does. So let's say the clock signal arrived here and the input A changed right when the clock edge occurred, and as a result this intermediate output AW went to a metastable state. Now when the metastable state came in, metastable state resolved within a time period less than the clock period. So the clock period is T, and essentially the sampling time, the settling time of the metastable state tau is smaller than the clock period. So as a result, by the time the second clock signal came in, this AW resolved into a logic state of 1. It could have been logic state 0 as well. It resolved into a definite logic state, and as a result, when the second clock pulse came in, this second flip-flop saw that okay, there is a stable state output, and as a result there was no metastable state that at any instance was seen in the final output AS. Alright, so essentially it represents a case when the metastable state was resolved before the flip-flop 2 was clocked. Alright, but as we have said earlier, this settling time, this tau, is an average quantity, meaning that on average the probability that this metastable state will be resolved within a time period of tau is very high. But it can also be the case that the time it takes for resolving this state can be much longer than tau, and essentially this is the situation that is being shown here. In this case, this signal AW is still in the metastable state when the flip-flop 2 is clocked, and as a result what will happen is that in this case there is a certain probability that this metastable state will propagate into the final output of the synchronizer AS. Alright, so essentially this says that in a 2 flip-flop synchronizer there is a certain probability that this metastable state will still be propagating to the rest of the circuit. So what we are going to show next is that how we can find out the probability that in a certain synchronizer, for a certain synchronizer configuration, the metastable state will propagate to the rest of the circuit. And what we will see is that by putting 2 flip-flops we can reduce the probability of the, so compared to 1 flip-flop, if there are 2 flip-flops, then the probability of propagation of this metastable state goes down significantly, and if we add 1 more flip-flop over here, then the probability will go even further. And that's how we design synchronizers such that the metastability conditions do not, for all practical purposes, propagate to the rest of the circuit. Alright, so let's first set up the mathematical framework for calculating the synchronization failure. So the mathematical framework goes as follows. So the probability of failure due to metastability in one cycle is given by PF, and this PF is essentially multiplication of the probability of entering probability of the flip-flop of entering the metastable state in one cycle, PE, multiplied with the probability that the system, the flip-flop, will still stay in a metastable state during a time period of TW. Alright, so let's look at the individual components. So first of all, how does a flip-flop enter into a metastable state? It enters into a metastable state if the clock signal changes, if the input changes during a time window equal to that of the hold time plus the setup time of the flip-flop. So if the clock period is TCY, then the probability of entering the metastable state is sample time plus hold time divided by the cycle time, which is the period. Alright, so essentially the probability of a given transition being in this setup plus hold window. So that's that. So that is given by this ratio. Alright, and then what is the probability that once that the flip-flop has entered into this metastable state, it will stay in the metastable state for a time period of TW, and that probability is given by exponential of negative TW over tau. Alright, so this is essentially a phenomenological model, but for all practical purposes actually it works. Alright, so let's look at a very quick example. So let's say the clock frequency is 1 gigahertz, so T cycle is 1 nanosecond, and the sample and hold time are both equal to 10 picoseconds, and the settling time is 50 picoseconds. So the time window for within which the metastable state has to be resolved is the cycle time minus the sample setup time minus the hold time. So this gives us to be 0.98 nanoseconds. So the probability of the system entering into the metastable state in one cycle is this TW over the cycle period or the clock period, which is 0.02. And then the probability of the flip-flop staying in the metastable state is e power minus tau over minus TW over tau, which comes out to be 3 point something into 10 power minus 9. So the probability of failure in one cycle is 6 point something into 10 power minus 11 per cycle. Alright, so now let's calculate that what is the probability of the flip-flop not failing within one cycle. Okay, so in this case we are actually considering a two flip-flop synchronizer, and what we are saying is that probability of not failing in one cycle essentially means that the probability that within one cycle the final output of the two flip-flop synchronizer will not go into a metastable state. So within one cycle the probability of having a metastable state, that the output in one cycle is PF. So the probability of not failing is 1 minus PF. Okay, so then the probability of not failing in n cycle is 1 minus PF to the power n. Okay, so now if we take this number and calculate 1 minus PF for different cycles, these are the numbers we will get. Now for 10 power 3 cycles, you see that the probability will probably not fail, because the probability of not failing in 10 power 3 cycles is very close to 1. But again, because this cycle comes in the exponent, what happens is that this number quickly deteriorates as the number of cycle increases. So by 10 power 9 cycles, which is equivalent to 1 second because the frequency is 1 gigahertz, the probability of not failing actually becomes significantly smaller than 1. So there is a 6% chance that the two flip-flop synchronizer will fail within 1 second is actually 6%. 1 minus 0.94 is 0.06, which is 6%. But within 10 cycles, within 10 seconds or 10 power 10 cycles, the probability of failure reaches 50%, and within 10 power 11 cycles, which is 100 seconds, the system will definitely fail because the probability of not failing is very close to 0. So in this particular example, what we are essentially seeing is that the system cannot prevent metastability failures. and prevent metastability failures. So what we essentially need to do is add one more flip-flop to the system, to the synchronizer, such that the probability of failure actually goes up significantly, not failing goes up significantly. Alright, so for that what we will essentially do is, if we have a third synchronizer, this time window for resolving will increase. So let's look at the case. So essentially what we want to look is, how much difference does one extra flip-flop make? So essentially all the analysis up to this point are the same. Now because you have added one third flip-flop, the amount of time that you have to resolve the metastability becomes double because of a third flip-flop, and essentially you get the probability of staying in the metastable state now becomes 10 power it's close to 10 power minus 18. In the previous case this was 3 power minus 9. So essentially by doubling the time you have reduced the probability of the systems or the final output being in the metastable state by 9 order of magnitude. And then if you again do all these calculations, you can actually see that by adding a third flip-flop, the probability of not failing, the probability of this synchronizer not failing within 10 years is actually very close to 1. In fact, if you do the calculation, you will see that within the framework of this analysis, even without 3000 years, this system, the probability of this synchronizer failing is actually just 1.5% within 3000 years. So again, the whole point is that you can avoid metastability failures by adding extra flip-flop in the synchronizers, and these synchronizers are essentially used for communications between individual clock domains.